We're going to spend quite a bit of time talking about oxidation reduction reactions because these tend to be the most common type of reaction that occurs in a chemical reaction. This is also known as a redox reaction. It's just the RED stands for reduction and OX is oxidation. And this deals with the transfer of electrons. And if you think about it, this is why it's so common because, we can't change protons or neutrons in the nucleus, or at least through conventional means. But the only other thing that's available to do chemical reactions is really electrons. And so moving electrons from one atom to another or from one compound to another is kind of what all reactions are about. So I kind of gave a primer of redox in lab, but I am going to go through a lot of the foundational concepts here. So oxidation is the loss of electrons, and reduction is the gain of electrons. Now, the reason I capitalized some of the letters in those statements is to give you a little bit of an acronym to remember what oxidation and reduction is. Oil rig, oxidation is the loss of electrons, and rig stands for reduction, is gain of electrons. So let's look at an example. And this is something that you did in lab. Took zinc metal and put in a solution of iron, 2 ions, and that zinc metal was converted into zinc ions, and the iron ions were converted into iron metal. Now we would say that the zinc got oxidized because if we look at what happened to it, it lost electrons. And if we look at what happened to iron, iron went from +2 to 0. In order to do that, it gained electrons. So we would say that the zinc metal got oxidized. And we would say that the iron ion got reduced. Now, one of the ways that we more commonly label these substances is it's like a game of opposites. If zinc got oxidized, if it lost electrons, then it's causing iron to get reduced. So we call zinc the reducing agent. And we call the iron 2 cation the oxidizing agent. Now, you might hear another term for this. A reducing agent, also known as a reductant, same means the same exact thing. It's just another way to say it. And an oxidizing agent would be called an oxidant. So you might hear me use those interchangeably, those two terms interchangeably. So just be familiar with them. Now, one of the ways that we recognize what has gained electrons, what has lost electrons, is to look at what's known as the oxidation state. Because sometimes it's difficult to determine if an atom, especially nonmetals, gain or lose electrons. And we can use oxidation state or oxidation numbers to help us. This is just simply another way to count electrons. And I want to highlight that this is not formal charge. So let's look at some ways that we have used to count electrons in the past. we looked at how many valence electrons are around an atom. So let's take carbon dioxide, for example. The way we counted valence electrons is a lot of times we ended up double counting them. So if we look at how many electrons are around this carbon, we got 8 of them. Now, if I were to ask you to do the same for the oxygen, what would you say? Well, we would say there's 8 electrons around the oxygen as well. We're double counting these electrons in the middle. We're counting them for carbon for valence electrons, and we're counting them for oxygen for valence electrons. Now, another way that we looked or that we counted electrons was to calculate formal charge. So again, I'll draw carbon dioxide here. And the way we calculate formal charge, like for example, the carbon, is we take its number of valence electrons, we get that off the periodic table, okay, minus the number of bonds it has around it, then minus how many non-bonding electrons there are. So the formal charge for carbon was 0. And then for oxygen, so oxygen atom has 6 valence electrons. It's got 2 bonds to it, and then 4 non-bonding electrons. It also has a charge of 0. But what formal charge assumes is that electrons in a bond are shared equally, which now that we've talked about electronegativity in the past, we know that that's not necessarily the case if one atom is more electronegative than the other. Now, how does this relate to oxidation state? The oxidation state or oxidation number, we pretend that all bonds are ionic. And then we say the more electronegative atom gets all the electrons in a bond. So let's use carbon dioxide as an example again. And what I'm going to do is I'm going to kind of split them up like this. And all oxygen here on the right is going to get all the electrons in the bond. And this oxygen gets all of the electrons on that side. And carbon is left with none. So the way that we calculate its oxidation state is we take the number of valence electrons from the periodic table minus the number of non-bonding electrons. So for carbon, that's 4 minus 0. Its oxidation state would be +4. And then for oxygen atom has 6 valence electrons. That one has 8 non-bonding electrons around it. It has an oxidation state of -2. Basically, what oxidation state allows us to do, it helps us to identify where the electrons are. Now, I will mention that you probably will not ever do this kind of calculation. In the next video, I'm going to go over some of the ground rules or tips, so to speak, on predicting and calculating oxidation numbers. And well, I'll just leave you with this kind of thought. Neither formal charge or oxidation state is 100% correct. It's somewhere in the middle. But we use either one to help us count electrons for different uses. And when it comes to redox reactions, we're going to use oxidation state to really tell us where the electrons are and help us figure out where the transfer of electrons is occurring.